Welcome to my live stream. Welcome. I'm brushing my hair right now. I'm brushing my hair. The goal of this chapter is to provide a the goal of this chapter is to provide a comprehensive The goal of this chapter is to provide a comprehensive review of the fundamental concepts of fractional calculus in addition to several fixed constraints that they are essential for development of the subsequent part of this work. It presents the main property of the special functions, fractional integral, and fractional derivative. Basic spatial functions in fractional calculus. In this section, we present the basic properties of certain special functions. In particular, we focus on the gamma beta Metaglypher function, Metaglypher function, which play an important role in our study of fractional derivatives and fractional differential equations. The gamma function. The gamma function is well known that the Euler gamma function is one of the fundamental functions in fractional calculus since it extends the concept of the fractional uh, the concept of the factorial and factorial to non-integer and even complex value of n. Definition: the gamma function, gamma of v, is defined by the integral gamma of v equals the integral from 0 to infinity e to the power of z minus 1, e to the power minus t, where the integral is with respect to t. Z is in the complex number such that the real value of z is strictly positive. Properties of the gamma function. A fundamental property of the gamma function is its adherence to the following fractional equation. For all z with a real part of z is greater than 0, gamma of z plus 1 equals z gamma of z, which can be easily proved by the integration by parts. The gamma of z plus 1 equals to the integral from 0 to infinity with respect to t of e to the power of minus t to the power of z, which equals to minus e to the power of minus t times t to the power of z, and the borders of the integral are t equals 0 and t equals to infinity plus z times the integral with respect to t from 0 to infinity e to the power of minus z t to the power of 3 minus 1 is equals to gamma of z is gamma of 3. Obviously, gamma of 1 equals 1, and using this equation, we obtain that z equals to 1, 2, and 3, and so on. So here there is a mistake. It's supposed to be gamma of 4 equals to 3 times gamma of 3 equals 3 factorial. The beta function. The beta function is one of the essential functions in fractional calculus, and it plays an important role when combined with the gamma function. Definition. The beta function represents a type of polar integer defined for the beta function. The beta function represents a type of polar integer defined for all complex number x and y with strictly positive real part by beta of x y equals to the integral from 0 to 1 e to the power of x minus 1 1 minus t to the power of y minus 1 dt. X and y are complex numbers. I can't stop this hiccup. such that the real part of x is greater than 0 and the real part of y is greater than 0. Ah, the beta function can be written in the terms of the gamma function as follows. Beta of xy equals gamma of x gamma of y over gamma of x plus y, where the real part of x is greater than 0 and the real part of y is greater than 0. Some property of the beta function. The most important property of the beta function are the beta function is symmetric. Symmetric. The beta xy equals the beta yx, where the real part of x is greater than 0 and the real part of y is greater than 0. Recursive relation. Beta of x plus 1 y equals to x over x plus y times beta of x y. Beta of x y plus 1 equals to y over x plus y times beta of x y. Beta of x plus 1 y plus beta of x y plus 1 equals to beta of x y. Special value. Beta of 1 as y equals 1 over y, and beta of x y 1 equals to 1 over x. Connection with binomial coefficients. Binomial coefficients. Beta of xy equals to x plus y minus 1 factorial over x minus 1 factorial y of minus 1 factorial. Meta-Glyfer function. The classical meta-Glyfer function introduced and studied by the Swedish mathematician Gösta Meta-Glyfer in the 1903 as generalization of the exponential function e to the power of x. It plays a fundamental role in the theory of fractional calculus. The Meta-Glyfer function is defined by the following power theory. The Meta-Glyfer function of order alpha with respect to x equals to the sum from 0 to infinity of x to the power of k over gamma of k times alpha plus 1, where x is in C, alpha is greater than 0. Another definition, then the generalized Meta-Glyfer function is given by A alpha beta of x equals to the sum from 0 to infinity x to the power of k over gamma of k alpha plus beta. X is in the complex number. Alpha and beta are both greater than 0. Formulations with classical functions. Now we present some relation with classical functions. It's the Meta-Glyfer uh, function of order alpha 1 equals to the sum from 0 to infinity. Some relation with graphical function. Now we'll present some relation with graphical function. E to E of alpha 1, E of x equals the sum from 0 to infinity, x to the power of k over gamma of k alpha plus 1, which is E to E of x. The Mittag-Leffler function of order alpha equals 1 and beta equals 1 is the Mittag-Leffler function with parameter alpha equals 1, which equals to the exponential function e to the power of x. The Mittag-Leffler function of 2 with parameter alpha equals 2, beta equals 1 of x is equals to cosine h of the square root of x e to the Mittag-Leffler function of parameter alpha beta, alpha equals to 1, beta equals 2, equals e to the power of minus 1 over x, and so on. Fractional integer and fractional derivative. In this section, we present the definition and some property of various types of fractional integer and fractional derivative. Riemann-Liouville fractional integer. The definitions and property of fractional integer and derivatives that are going to be presented can be found in a number of interesting books such as definition. Let alpha is greater than 0 and y be a function defined on the interval t1, t2. The left Riemann fractional integer is defined by Riemann fractional integer from t1 plus of order alpha of y of t equals 1 over gamma of alpha times the integral from t1 to t2 of t minus x to the power of alpha minus 1 of y of x dx. T is greater than a. The right Riemann fractional integer is defined as follows. We are almost gonna finish the first Pomodoro. That's progress. We'll take a break. I'm on my break now. Let's read some verses of the Quran. Take a sip of the coffee. Black coffee. Black coffee. Let's start another Pomodoro. So here we'll just I'm just reading, and this is the step one is to read. Definition: let alpha greater than zero and y be a function defined on the intervals t1, t2. The right Riemann-Neuville fractional integer is defined by the right Riemann-Neuville fractional order of order alpha of y of t equals the 1 over gamma of alpha times the integral from t1 to t2 of the kernel is t minus x to the power of alpha minus 1 y of x dx. The right Riemann-Neuville fractional integer is defined as follows. The right Riemann-Neuville fractional integer is defined as follows. The right Riemann-Neuville of order alpha of y equals 1 over gamma of alpha times the integral of from t to t2. The kernel is x minus c of order alpha minus 1 y of x dx. Fractional integers are defined for functions in L1, existing almost everywhere. Let alpha is greater than 0 and n is a natural number, but it doesn't equal to 0, such that n minus 1 alpha is between n minus 1 and n. The right Riemann usual fractional derivative of order alpha of a function f in the uh, continuous function space is defined as follows. Riemann usual the right the left the right no the left Riemann usual of fractional derivative of order alpha of f equals to the the the, the nth derivative of the integral of the right of the left Riemann usual fractional or integral of order n minus alpha f of t, which equals 1 over gamma of n minus alpha times d of t to the power of n times the integral from a to t minus s n minus alpha minus 1 f of s dx. The left Riemann derivative of order alpha of f is defined by the left Riemann of order alpha from the uh, beta f equals to minus d to the power of n minus the derivative or to the power of n times the integral from b minus to n minus alpha f of t, which equals 1 over n minus alpha times minus the derivative of order n times the integral from t to b s minus t n minus alpha minus 1 f of s dx. Adamard fractional integer and derivative. Here we present the Adamard fractional integer and derivative. We outline some key properties of this operator. Let alpha greater than 0 and let a b, where a b are between a and infinity, and definitely let not infinity, be a finite or infinite interval. The Adamard fractional integer of order alpha for a function f is defined by the Adamard fractional integer of order alpha of f of t equals 1 over gamma of alpha times the integral from a to t, the logarithmic t over s of to the power of alpha minus 1 times f of s over s dx. Caputo fractional derivative. The Caputo fractional derivative is almost a recent concept that remind you will fractional derivative definition. The definition goes like this. Let the left Caputo fractional derivative is given by the left Caputo fractional derivative of order alpha equals 1 over gamma of n minus alpha. The integral of the nth derivative of z times t minus z to the power of n minus 1 minus alpha with respect to z. Similarly, the light Caputo derivative is given by 1 over gamma of n minus alpha, the integral from t to t2, the nth derivative of y times zeta minus t to the power of n minus alpha minus 1. The differential operator is named after Caputo, who is generally credited with being the first to introduce it in the context of application to study some of its properties. This operator has properties that differ from those of the Riemann-Wheel fractional derivative. For instance, the Caputo fractional derivative suits a linear operator and possesses the commutation property that is the Caputo fractional derivative of order alpha times the Caputo fractional derivative of order beta of y equals to the the left Caputo fractional derivative of order beta times the left Caputo fractional derivative of order alpha of y, which equals the sum of alpha plus beta. The remind you will the fractional derivative over linear, it is generally do not commute. Some properties, linearity, let n minus 1, let alpha between n minus 1 and n, let and lambda mu are in the complex number. Theorem. In this section, we state several theorems we will use in the subsequent development of our work. Schauder fixed point theorem. Schauder fixed point theorem. We use Schauder fixed point theorem in the following form. Let the space X muted with the norm be a Banach space over I'm tired. Let's fix let's do this theorem finish this Pomodoro. It's only in 8 minutes. 8 minutes left. Okay, what is Schauder fixed point theorem? Schauder fixed point theorem states if there is a space, let X be a Banach space over K can be a natural a real number or a complex number, and let X be in subset in X. S is a subset in X, and it is closed, bounded, convex, and non-empty. Closed, bounded, convex, and non-empty. Closed, bounded, convex, non-empty. Closed, bounded, closed, bounded, convex, non-empty. Any compact operator has at least one fixed point. So the Arzola-Ascoli theorem, let I be an interval from T1 to T2 be closed bounded interval. F of the continuous function on the interval E is relatively compact in C equipped with the strip norm F and only F. F is uniformly bounded. There is just an M that our F is less than M for all F in the tribute F and all T in the interval I. Equicontinuous for every epsilon greater than 0, there exists delta upward greater than 0 and dependent of f such that t minus f is less than delta implies that f minus f is also less than epsilon for all f in the tribute f. Banach contraction principle theorem. Let X be a complex metric space. A mapping F from X to X is called the contraction if there exists K in the interval 0, 1 such that oh my god such that the distance between f of x and f of y is less than d less than k, the distance between x and y for all x and y in the space x. Then f admits a unique fixed point in x. Okay, now we read the chapter 1. Later on, maybe we will read the chapter 2. And now I have to finish this study section because I'm tired. Okay, let's start. We will be back later on.